Okay, let's dive right into this explainer and demystify the completely wild, highly complex regulatory framework of explosive atmospheres. I mean, if you've ever looked out at one of those sprawling offshore oil rigs and wondered, how on earth do thousands of electrical instruments operate safely when they're literally surrounded by highly volatile hydrocarbons? Well, you are definitely in the right place. Today, we're taking a really structured journey. We're going from the theoretical rule books all the way to the physical, heavy steel decks of some of the world's absolute largest offshore vessels. Whether you're just starting out in the industry or you're actively on the career pathway to becoming a CompEx or ATEX certified design engineer, mastering this blueprint is your absolutely essential first step. Let's get into it.
So here's our quick roadmap for the explainer today. First up, the foundations of hazardous areas. Second, decoding the zone system. Third, equipment selection and X protection. And finally, we'll look at offshore facilities in action.
All right, kicking things off with Section 1, Foundations of Hazardous Areas.
You know the classic fire triangle, right? Mix fuel, oxygen, and an ignition source, and boom, you've got a disaster. Well, in our world, the whole game is about eliminating that ignition leg entirely. But when you're dealing with millions of miles of global wiring and countless offshore platforms, how do you actually guarantee that? The answer is a strict, interwoven matrix of international standards. And these aren't just competing rulebooks. They govern entirely different physical domains. For example, the IEC directives lay out your general electrical installations, while DNV standards specifically dictate marine power and cable specs. Meanwhile, your API and IP15 codes, those are the ultimate authorities for mapping out petroleum facility locations. Working together, these documents form the global law. They standardize exactly how we calculate risk based on tricky variables like vapor density and gas grouping.
Now, take a look at this number, 200 degrees Celsius. That happens to be the extreme operating temperature of the glycol reboiler drum on the Pyrenees FPSO. To put that into perspective, that's almost twice the boiling point of water. Think about the reality of working offshore. You might have freezing ocean winds battering the deck, but right inside that specific module, you've got machinery running incredibly hot. In these hazardous areas, even the surface temperature of a piece of equipment can become an ignition source. No spark needed. To prevent this, every single flammable gas is assigned an ignition temperature, and equipment is strictly rated with temperature classes ranging from T1 to T6 to make absolutely sure it never crosses that critical threshold. So at 200 degrees, engineers have to rigorously specify the local equipment class so a seemingly harmless operational temperature doesn't just inadvertently spark a catastrophe.
Moving right along to Section 2, Decoding the Zone System.
So, we don't just guess where a fire might happen. We calculate it meticulously. When an engineer looks at a crazy, complex piping layout, they have to ask, how likely is a leak to actually occur here? To figure this out, they use what's called the point source method. This means engineers literally trace the lines on massive P&ID, that's piping and instrumentation diagrams. They go through identifying every single valve, flange, pump, and vent. By doing this, they can pinpoint the exact origin points where a hazard might be released in the atmosphere, and then they classify them by their specific grade of release.
And what you end up with is a really striking dichotomy of risk. On one hand, you have a Zone 0 continuous threat, and on the other, a Zone 2 unlikely event. Zone 0 is literally the belly of the beast. Imagine the dense, constantly volatile vapor space trapped inside a crude oil cargo tank. That's Zone 0. In contrast, Zone 2 is an area where a leak is a total anomaly. Maybe a secondary release from a blown gasket that's going to get repaired super quickly. And, sitting right in the middle of all that is Zone 1, which represents an area where a hazard might occur occasionally during just normal day-to-day operations. This whole gradation is brilliant because it allows us to target our engineering defenses exactly where they are needed most. But translating those dense API and IP15 standards into a physical reality on the deck requires a really methodical approach. First, you identify the source and grade of release. Then, you determine the fluid properties and, this is absolutely crucial, the ventilation conditions. This is a huge part of any ventilation assessment documentation. You can't just draw a theoretical circle on a blueprint and call it a day. The physical boundary of a hazardous zone expands dramatically if it's trapped in a confined, poorly ventilated module. Or, conversely, it shrinks if it's naturally ventilated out in the open ocean breeze. Finally, based on all that, you assign the appropriate zone and distance boundaries.
Okay, Section 3, Equipment Selection and X Protection.
Because look, once you've designated an area as Zone 1 or Zone 2, standard off-the-shelf electronics, they simply won't cut it. We have to utilize specialized armor to protect the equipment, and this 4 pillars framework makes memorizing these X protection methods pretty much effortless. We've got XD for containment, XP for separation, keeping gases out using pressurized clean air, XE for increased safety, making sure no arcs or sparks can occur in the first place, and XI for strict energy limitation. Let's actually break down a couple of the most common methods you're going to encounter out in the field.
So here is the crazy thing about XD'd flame-proof equipment. We aren't actually trying to stop the explosion here. Actually, scratch that. It's more like we are robustly containing it so it just doesn't ignite the external zone. With XD'd, the baseline assumption is that explosive gas absolutely will get inside the enclosure. If a spark ignites it, the heavy-duty metal casing is designed to just absorb and withstand that internal blast. But the real magic? That happens at the seams. They use these precision-engineered gaps called flame paths. These force the escaping fiery gases through this tight little metal maze, cooling them down to a temperature way below the ignition point of the surrounding atmosphere before they can even exit. It's just a brilliant brute force engineering solution.
Now, instead of using brute force to contain a blast, intrinsic safety, or XI, takes a totally elegant approach. It simply starves the system of energy. This method is heavily used for delicate instruments, like level transmitters sitting deep inside those Zone 0 crude oil tanks we talked about. Intrinsic safety uses specialized barriers to restrict the electrical voltage and current going out to the device. So even under catastrophic fault conditions, imagine a cable being completely sliced in half and short-circuiting. The resulting spark physically lacks the thermal energy to ignite the surrounding gas. It literally starves the spark before it can ever form.
And that brings us to our final section, Section 4, Offshore Facilities in Action.
Let's ground all this theory into reality by dissecting the actual hazardous area schedules for the Baobab and Pyrenees FPSOs. Floating production, storage, and offloading vessels, they process raw hydrocarbons right out of the ocean floor. That makes them the ultimate testing ground for this stuff. Let's play detective for a second. To build these hazard schedules, engineers have to cross-reference a staggering amount of data. We're talking fluid properties, operating temperatures, structural ventilation, all of it, just to dictate the exact safety requirements for thousands of individual components. Just compare the high-pressure fuel gas heater directly against the simple seawater filter on this slide. On the Pyrenees schedule, the fuel gas heater handles volatile processed gas that happens to be lighter than air. Because of this, it requires a Zone 2 rating extending 1 meter from its valves and flanges. But right next door on the spreadsheet, the seawater coarse filter is happily chugging along at 31 degrees Celsius with absolutely zero hazardous rating. This sharp contrast shows you just how incredibly targeted these engineering assessments have to be. We don't over-engineer where it isn't needed, but we fortify exactly where the threat exists.
On the Baobab FPSO, 3 meters is the standard horizontal and vertical Zone 2 boundary distance surrounding secondary releases in natural open-air ventilation. Whether you're inspecting the low-pressure gas scrubber, the flow-line circulation pump, or the flash gas compressor skid, time and time again you see this 3-meter safety bubble prescribed around potential leak points. And this metric isn't just theory on a page. It creates a highly visible, 3-dimensional map on the deck that strictly dictates where maintenance crews can and cannot bring standard, non-rated tools without risking a catastrophic spark.
But what happens if the mechanical ventilation just fails? Well, automated electrical systems must step in instantly. In the design philosophy of these massive offshore vessels, you might have an enclosed space relying on positive pressure to keep explosive gases out, which, if you remember, is a core principle of that XP method we covered. If that clean air fan fails, the facility doesn't just wait around to see what happens. No way. Immediate audiovisual alarms trigger, and power to any equipment not certified for that suddenly unprotected zone is automatically slashed. It forms this uncompromising automated web of redundant safety.
So as we wrap up this explainer, I want you to ask yourself, if a primary ventilation fan fails on your rig right now, are your hazard schedules robust enough to prevent a catastrophe? The line between safe, lucrative production and total disaster is drawn by the engineers who master these exact rules. If you're on the careers pathway to becoming an X or ATEX certified design engineer, mastering this blueprint is step 1 of your journey. Thank you so much for joining me today. Keep analyzing your environments, respect those boundaries, and stay safe out there.